We're now moving into fluids, and so the first video here is going to be related to pressure and density. Okay, so pressure is capital P, and that's force over an area. And so if you imagine like you have this area here, you have forces being pushed over the whole area, that is just what pressure is. And so, for example, if you have a sheet of paper on a table, there is actually the pressure of the force of the air pushing down on the sheet. The other way to write this then is that we could write it as force equals pressure over or times an area. So I just multiplied by A over here. So both are useful. One thing that you should know, like if you have a box, it's gonna, and you are working with some forces and areas here. If you have the area of the box on one side, that is enough. The pressure is going to be the same on all of the sides. So you only have to figure out for one side of the box. So like for example, if you know, and I should write this first, the pressure of atmosphere. This is just the regular pressure of air pushing down on us all the time at sea level at room temperature is 1.01 times 10 to the 5th PA, which stands for pascals, because Pascal was the guy who really spearheaded pressure like this. So some people write this as 1001 kilopascals. Some people, pascals are pretty small, so some people use kilopascals. But we're going to just use 1.01 times 10 to the 5th pascals. So for example, let's say that we have just a normal 8.5 by 11 inch sheet of paper. And we want to know what is the pressure being exerted by normal air pressure on that sheet. So the first thing we're going to do is convert to meters. Now I've already done this conversion, so I have 0.28 meters is the length, 0.22 meters is the width. And so when I multiply that out, the area is 0.0616 meters squared. Or that would be about, well, I would have to do the conversions to think about centimeters squared. Now, to actually figure out the force that is going on here with this sheet of paper, I'm going to use this top equation because I have pressure and I have the area. So the pressure is 1.01 times 10 to the 5th, and the area is 0.0616. Now I go to my calculator. When I crunch the numbers here, I get about, let me see here, I get 6221.6, which, let's say that it's going to be 6200, because we have two sig figs, 6200 newtons. Now something else that will come in handy here is that approximately 4.45 newtons equals 1 pound of force. So if I was to take that and divide by 4.45, that's about 1,393 pounds of force being exerted on a piece of paper. So this is a ton of force, almost literally. So why don't we feel this? What's going on here? Well, if you hold up a sheet of paper, you have this force going down on the sheet of paper, but also air pressure is equal on the underside. And so you're not going to see or experience this force. And it's kind of the same reason why our body does not buckle under the pressure there. Our body has the same force all over it. But there is some sense of a force pushing out on your from inside your body. So these forces can be really strong. There's another example that is pretty famous. There was a scientist a couple hundred years ago that would put these steel plates together kind of like this. they would meet here, and he would suck out the air, so basically the pressure was almost zero inside, very nearly zero. And then he would tie this side and this side to a team of horses, and he would have a competition to try to see who can pull the plates apart. The pressure was so great that it was an extremely challenging thing to do. So to figure out what is the amount of pressure here, or what force would you have to pull this thing apart, what we're looking at here is force equals pressure times area again. Now let's say that this has an area of 1 meter squared, the cross section of it. So it could be a circle that has an area of about 1 meter squared. We want to know what force would be pulling it apart. So we need to find the difference in pressure from inside and outside, and that would be what we use for the pressure here. But we know that the pressure inside is zero, so this is actually just going to be the pressure of the atmosphere times 1 squared, which that means that the force we have to actually exert is just going to be pressure times 1, which is, we know, 1.01 times 10 to the 5th, but with sig figs it's really just going to be 1 times 10 to the 5th newtons. Okay. Now if you divide that by 4.45, you're going to get about 22,472 pounds of force. That'd be 11 tons of force on that cross-sectional area. So no wonder it took teams of horses to pull those apart. Okay, so the other thing that we have to discuss is density. Density is always signified by rho. So it looks like a P, but it's the Greek letter rho. And rho is the mass of your object divided by the volume. And so you have this volume here, this box, and you're just asking how much stuff is inside this box per every box. In other words, how closely packed together is this stuff? Metals are going to be very dense. Lightly dense things are going to be like air. I think of like the difference between shipping a weight and packing peanuts in a box. The densities are going to be extremely different. And the densities here are going to be in kilograms per meters cubed. Okay, so this is also why water floats. The density of water is actually slightly less when it's frozen. So water, when it's frozen, is going to be slightly less dense, and the reason is because the volume increases. So if you have this much amount of water, you have so much stuff in there, and then when it freezes, it gets just slightly bigger, but it still has the same amount of stuff. It's going to be less packed together, and so that's why ice freezes. So one thing to keep in mind here is that density does require that you look at pressure and temperature. Those things will actually affect density. So, for example, density of water and salt water are different also, by the way. So this might explain why ships actually have different floating heights when they go from the Mississippi down into the ocean. Because depending on the compound, it's going to have different densities. So what I've done is I've created a sheet that I stole from the book that has common lists of densities that you can check out on our website.